during the study of data science and statistics, we focus slightly also on the mathematics, because in many applications, math is quite important, and definitely also in the field of statistics and data science. To, well, basically give you an idea of where it could be, where math is very important, is in machine learning. Well, probably you already heard about machine learning, and it's actually a branch of artificial intelligence. And like Garnet already also told you, it's really getting very popular, machine learning, artificial intelligence in the industry. Well, so for example, machine learning actually focuses on data and algorithms, so on the input, to basically imitate the learning behavior of humans. And the idea of using machine learning and a more specific part, actually deep learning, is to actually also improve its accuracy if we have more and more data available. So this also gives you an idea why data is important, and the more data we have, the more accurate our conclusions could be. Yeah, like already mentioned before, data science, and for example, in particular, machine learning and deep learning, is really getting popular since, well, the 1980s, but especially now, companies really have seen the importance of data science and statistics also. But of course, as I already told you, also the math behind it is quite important in order to be able to work with machine learning and deep learning and to improve artificial intelligence. But if we look at this graph, then we see that the popularity of linear algebra and calculus, the main tools of data science and statistics, and in particular machine learning and deep learning, have not really become much more popular. We really see that data science is really getting to know the industry, so the popularity, the word is really becoming, is really appearing a lot in newspapers, is really appearing a lot in books. And we also see that deep learning also since 2010 is really getting more popular. So this would also give an idea why actually the statistics and data science studies is maybe something that you're really interested in if you want to work at a company later. Well, so the idea of this talk, of this tiny lecture, is to give you an idea of what we, for example, teach in the course Mathematics for Statisticians. And instead of giving a introductory lecture, so the first lecture, I decided actually to give one of the last lectures of the course. And we are not typically focusing a lot on the mathematical details, but really the ideas behind it. So we'll get into a brief look at Taylor approximations. And Taylor approximations is a very useful tool, especially in the examples I gave you in deep learning and machine learning, but especially also in a lot of applications in statistics also. So to recall a little bit, because it can also be the case that things have faded away over the time. The idea of Taylor approximations is actually to recall what's actually the slope and what's actually a derivative. So first things first, a slope indicates the rate of a vertical change over a horizontal change. So the slope of this function with distance delta x is this purple line. And actually the idea, if we want to talk about a infinitesimal change, a change of the function in a certain point, we actually want to make this delta x smaller and smaller. We want to have some indication about what's actually the slope in a single point. So if we let delta x tend to 0, so to become it smaller and smaller, then we actually get some kind of idea about what's the slope in a single point, what's its tangent line going to be. So in a more mathematical notation, we can write the slope as f prime of x0, so actually the derivative of f, of the function f, so where f prime is the derivative. And recall a slope, but also the derivative, it measures some kind of sensitivity to the change of f. It really gives some idea about if a function is increasing or decreasing. I'm not really going to recall any kind of formulas and rules for the derivative, but keep in mind, if a function would be, for example, the distance of a car, then the derivative, for example, would be its velocity. It really tells us something about the change, a change in direction, a change in speed, whereas the slope does also. So what I meant with making delta x smaller, we really see that we eventually obtain a slope in a certain point. Okay, so I already mentioned this before, a tangent line. So the idea, if we have a slope in a point, we can draw a line. So a line would be of this formula, y equals ax plus b. And a would be the slope in a certain point, and b would be the intersection with the y-axis. So if we were going to draw this tangent line a bit further, then over here we have the formula of this tangent line, ax plus b. A is the slope of the function of the blue curve, and b would indeed be the intersection with the y-axis over here. And how do we find a and b? Well, as mentioned before, a is the slope in a single point, so it would be the derivative of the function. So f is this blue curve, and then the derivative, and then evaluated at x0 would be the slope in the single point, the gradient. And in order to obtain b, we use the formula, we rewrite this formula as b equals y minus ax, and we plug in this coordinate. So at x0, y equals fx0. So y equals fx0. Well, recall a is this one, and we plug in x, which is x naught. So we have found a and b, and we know the exact formula of this tangent line. So in one mathematical sentence, if we can approximate this function f with its tangent line, and this tangent line has this function, namely, recall this is ax plus b, and we can rewrite again this function like this, because the middle part we put it in on the left hand side, and these two have the same term in front of the x and the x naught, so we can rewrite this as this. So to put all this this story into a picture, we have a nice blue curve, we have this tangent line, and what I'm telling you guys right now is actually that this function can be nicely approximated around this x naught by simply a straight line. So if we are close to x naught, then, well, why would we even bother to look at this more general function? Because we can just look at this straight line, and, well, a straight line is not a particularly difficult function, so it's actually nicer to do, for example, calculations with a straight line instead of this more difficult function. But then again, if we would get quite far from x naught, so like here or here, the approximation is not very good. It differs too much. So the linear approximation, or the tangent line, is also called a first order Taylor approximation of the certain function f around a certain point. So the next idea is actually, could we do better? So could we approximate any function with a more relatively simple function? So indeed, the first order approximation the name already gave it away. Maybe there would be something like a second order approximation of a function. So how can we improve our accuracy by incorporating more derivatives? As explained previously, well, if f would be the distance traveled by a car, then its derivative would be its speed, but we can also look at the acceleration of a car, because the acceleration would tell us something, for example, about the curvature of a function. So how would we do this? Well, it turns out to look at this function, this approximated polynomial. And why this one? Well, that's actually quite a different story, because then we have to dig deep into the mathematics, and I promised not to do that, because then we have to look at what kind of differentiation rules were there again. So I'm just giving this approximation and tell you, okay, so this polynomial, the reason why it's a polynomial, by the way, is that we can write it like ax squared plus bx plus c, and then a would be this number, b will be this number, and c will be something completely ugly. So I didn't write that one down. So this is a polynomial, like ax squared plus bx plus c. And what the rest of the talk, I'm trying to convince that this polynomial is even a better approximation than the linear approximation. And the reason behind this is actually that we have some value at a certain point. We look at its speed, but we also look at the acceleration, at the curvature of a function. And by also taking the curvature into account, we perhaps can approximate a function better. So this specific choice of a polynomial is also called a second order Taylor expansion. And of course, we can also do this even further, like a third order, a fourth order, or a fifth order, etc. So a more general definition, and this formula may look a bit scary, but it's actually the same as we have seen before. If the first order Taylor expansion is only the first two terms, the second order Taylor expansion is the second term, but we can also add more terms. So we add more derivatives, and more derivatives means more information. And note that actually P0 is just the value of f at that certain point, and P1 is actually the linearization, the linear approximation. So to put things into a picture, why are we actually talking about this Taylor approximation? What does it do? Well, higher derivatives add more information for a broader interval around x0. So what we're now going to do, we have this function fx, which is 3 to the power x. This function looks like this blue function. And this red one is right now the 0th Taylor approximation. If we now add an extra term, then we have got our linear approximation, our tangent line. And it's already quite nice approximation of actually the general function 3 to the power x, near 0, of course, because if we look at, for example, x equals to 2, then already the difference is quite big. But if we're going to add even more terms, so the second order approximation, it's already quite nice to see that it's really trying to coincide. But still, at x is 2, for example, the difference is still quite big. But if we keep on adding more terms, so that corresponds to the formula that I showed you, we can just add more terms and see that actually this approximation is becoming very well. And now the main question is actually, okay, so why won't we just work with 3 to the power x? Why do we want to work with these Taylor approximations? Well, the main reason is actually because it simplifies the calculation. And for example, computers find calculations with polynomials easier than with more general functions like 3 to the power x, or the square root of x, or the sine of x. These functions are actually quite difficult, and computers find it much more easier to work with simple polynomials, so to say. Actually, also the Taylor approximations is really slightly hidden, but it's really the underlying principle for some optimization algorithms like gradient descent, Newton's method. These are all kind of algorithms that are very important for example, machine learning, deep learning, etc. So this idea of approximation plays a very significant role in all these applications. So to give you a more concrete idea, suppose we have a function for which we actually want to know the value of a function at a certain point C. So for example, if I would ask you what would be the sign of 0.1 or what would be the square root of 99? Because if I give you a pen and paper, then it's actually quite difficult to calculate these numbers, right? Well, actually, it turns out to be not that very difficult, and you don't even need a calculator to do this. Because actually, what I'm going to show you now, so with these Taylor approximations, a calculator itself, so if you use a calculator and you would ask, what's the square root of 99? It's actually not really calculating the square root of 99, but it's using polynomials. It's using, for example, Taylor approximations, Taylor polynomials to actually give an approximation of the square root of 99. Okay, so two important steps for this strategy. Okay, sometimes we know a value of a function at a certain point, and we actually now hope that we can use this value that we know to approximate the real value. And suppose f, when it's differentiable, we can use its derivatives. So we have already seen before, if we implement more and more derivatives, then the approximation is going to be better and better. And we're going to use Taylor polynomials. So if you look back at step 1, more explicitly, so suppose we are interested in the function, the square root of x. And if I'm asking you, okay, what's actually the square root of 99? Then what's this special point that I've been talking about? Well, the special point is actually 100, because the square root of 100 is not that difficult to calculate because it's just 10, because 10 to the power 10 times 10 becomes 100. Okay, now that we have found this special point, how can we ever actually calculate the square root of 99? Well, okay, so this is something that you just have to believe me, and if things are still fresh in your mind, then you agree with me, but otherwise, this will be something that we also learn during the masters. Is, well, I'm now claiming that the square root function, a function that occurs a lot in as well in academia as in applications, but the square root function is as many times differentiable as you want. It's a very nice, smooth function. It's a function that makes you happy. And if we have this function f, then it's, suppose this would then be a function that describes the distance traveled by a car, then this would be the function that demonstrates the speed, the velocity of a car. And then the second order derivative would then actually tell what the acceleration of this car is. Well, why these formulas hold, that's something that we will discuss in class. But just believe me, if f is this function, then f prime and f double prime will be these functions. And what we are now only going to do is actually use the formula of the Taylor polynomials. So let us write out actually the polynomial that we were interested in. Well, P2 was actually this polynomial, so f of x naught plus the first term, which actually described the tangent line of a function, plus the second magic term. And what we're now going to do is, well, because 99 is very close to 100, we're actually going to plug in 100. 100 is going to be the point that we use as reference point, and plug this into our formula. So x naught equals 100, so we have the square root of 100 plus the first derivative, which appeared to be this function, and plus the second derivative, which appeared to be this function, and then we plug in for x naught, we exchange this one with 100. And a simple calculation then shows that this can be simplified with 10 plus 1 divided by 20 with x minus 100 and this term. Okay, well, we are now actually almost finished, because in order to calculate the square root of 99, then we use this polynomial to approximate the square root of 99. And how do we do this? Well, we simply fill in x equals 99. So we now have a polynomial, and suppose you would now write down this polynomial on your pen and paper, and you would do plot this in your graphical calculator or in the computer. It really seems that this function coincides with the square root of x near 100. So we plug in 99, and by calculation, we see that this value equals to 79,599 divided by 8,000, which is equal to 9.949875. So actually, the main question is, what's actually the value of the square root of 99? Well, of course, the Taylor polynomial is just an approximation of the real function, so it does not necessarily give the exact value of f of x. So if the error function, something that occurs a lot in many courses, is defined actually as the real function minus the approximation function. And now, well, we found, for example, that the Taylor polynomial evaluated at 99 is approximately 9.949875. But if we would plug in the square root of 99 in our calculator, it says actually that it's 9.9498735. So apparently the second order Taylor polynomial is already quite a good approximation, because the 1, 2, 3, 4, the first 5 numbers after the digit coincide. So plugging this into this formula, the error function, we see that the error equals to 6.3 times 10 to the minus 7, which is a very, very small number. So basically the conclusion would then be that we actually have found a very good approximation of the square root of 99 by only using actually polynomials. And well, it only took me about 15 minutes to explain this example, but you can imagine how fast a calculator is, and because of the polynomials, these calculations happen so fast that you just press enter and he already gives you a good approximation by, for example, not calculating a second order Taylor polynomial, but for example a 10th order polynomial, because then you're already sure that the error is negligible. So in conclusion, why is this actually all true? Well, we have over here the theorem of Taylor, because we have Taylor polynomials. It's by the famous mathematician Taylor. And this theorem tells us that if a function is sufficiently smooth, so a very nice function, then it can be approximated by this polynomial that we've seen before, the Taylor polynomial. And we can just say that f of x is approximately the Pn of x, because the error is guaranteed to be small when n is sufficiently large. The reason for saying that this is actually the informal theorem is basically because guaranteed to be small and for sufficiently large are quite vague terms. So that's why it's called now the informal theorem, but things can be even more formal than this, but that's beyond the scope of this short lecture. So in conclusion, what did we find? Well, if we add more and more terms, we see actually that the error is really going to be negligible. And that we also have seen that actually calculating with polynomials is relatively easy compared to working with very difficult functions like 3 to the power x, or as we have seen in the previous example, the square root of x. But you can imagine that there are many more functions, and especially in applications, especially in the industry, they're working with phenomena that are even very, very difficult to even describe this with a certain function. So you really need to have approximations of real life in order to be able to draw conclusions. Well, I think this is it. I want to thank you very much for your attention. If you have any questions, please don't hesitate. Thank you.